Greetings, STEM 1 students. What I want to teach you about today is called factoring the difference of two squares. What I'll ask you to do is to take some notes, and if you look over here to the right, there are 8 questions. We're going to do 4 together, and then I'm going to have you do the last 4, and those last 4 are the ones that you're going to check with the teacher here before we transition today. So we'll see how it goes. All right. If you want to start this first section over here, you don't have to take any notes on. This is the content that is in that pink factoring guide. And so I would have that out while you're working on your factoring. I think that's going to be beneficial to help you kind of look for patterns, okay? So first thing we're going to do today is we're going to check to see if the two terms, we're going to be working only with 2 terms, to see if they have a greatest common factor. And if they do or don't, either way, we're still going to ask ourselves how many terms do they have. And if there are 2, we're going to learn what's called difference of two squares. But I just wanted you to point to where on your factoring guide we're kind of focusing today. And over here, this is where we're going to actually kind of learn about what that fancy looking formula actually means. Okay? So to get us started, I want to give you this thought process here. So if you want to go ahead and pause the video and jot this structure down, at least get this heading, and then we can add this in later to make sure you have room for it. But go ahead and get this heading added, and once you get that done, you can unpause your video. Now that you've had a chance to get the structure set up, what is a perfect square? All right, well, I'll give you some examples. 25 is a perfect square. 16 is a perfect square. R to the 8th z to the 4th power is a perfect square. Some non-examples would be like 20. R to the 3rd. P, J to the 5th. That's not considered a perfect square. So what I'm hoping you notice is when you look at the different columns, the left column can be broken down into 2 factors that are the same number or same value that when multiplied together give you the left-hand side. So here, 25 could be broken down into 5 and 5. In other words, here's a fancy word here. I think we made this one up last year. A perfect square is square rootable. In other words, when you take the square root, you get a whole number. You don't get any decimals. We don't get any remainders. We get a whole number such as 5. All right, you'll notice the same thing happens with 16. We can break that down into 4 and 4. So if you square root 16, we get the 4. All right, R to the 8th, z to the 4th. This is a perfect square because we can break it down into 2 parts, 2 factors that multiply to give me r to the 8th. And so when you're dealing with exponents, square rooting is really like cutting the exponent in half. Because r to the 4th times r to the 4th, when you add those together, we get 8. Okay? Same thing with the z. So anything that's an even number for an exponent is a perfect square. You can take the square root of an even exponent. Where here, there's nothing, I can't take p times something else and get p. There's nothing that is the same value that's going to generate p. Same thing with j. J to the 2nd. What would if you did second and second, we'd only get 4. So notice odd numbers, odd exponents aren't perfect squares. Odd exponents aren't perfect squares. And that's why, like on the left-hand side, anything with an even exponent is. 20 would not be a perfect square because nothing times itself gives you 20. Okay, so before we do the last examples over here, I want to show you kind of how to set each of these up. So you'll notice on your factoring guide, you'll have an expression that looks like this where it says a squared minus b squared. Basically, these numbers have to be perfect squares. Okay, and our word that we used to describe that was square rootable. That is by no means a mathematically scientifical word here, but it is a way to kind of think about it. If you can take the square root of it and not have any decimal values, or you get an integer, then this is a good case for the difference of two squares. The other thing that has to happen is it has to be subtraction. So if you want to circle that sign, it has to be subtraction. It only works when you're subtracting two squares. When you're adding two perfect squares, you just can't factor them. Okay? So what do? Basically, you square root the first one. So at whatever term comes first, you square root the first one. Okay? And then whatever comes second, you square root that one. So I'm just going to put square root of the second term. And then you do one where it's addition and one where it's subtraction. And basically that's it. It's as simple as that. You just have to check to see if it fits those conditions. So we'll go ahead and give these a try. All right. This is kind of the premise of everything we're going to be doing over here. So I'm going to kind of change the camera angle here. Come over. When we look at these examples, you're looking for two things. And I'll have you kind of write this in the side. Actually, let's add it to your factoring guide. So I'm going to turn this back this way. And on your factoring guide, I'm going to have you add a note here. Difference of two squares, really, you have to ask yourself two things. First question is, are they subtracted? And are they perfect squares? Some people say square rootable. That makes more sense. Write that down. I'm just going to put, are they perfect squares? But yeah, you could just ask, can you square root each number? Are they square rootable? Are they perfect squares? All right, so let's look at the ones we have over here. First question. Is it subtraction? In this case, yes, it is being subtracted. Are they square rootable? In other words, can you square root each of those parts? Yeah, I'd say you can square root each of those. So I'm going to do a little bit of color coding here. Grab my blue marker. So difference of two squares basically says you can do two binomials where you're just going to square root the first one that I have in red. So what times itself gives you x squared? X and x. All right, and then if you look at the 9, what times itself gives you 9? 3 times 3. And I'm just going to put one as a plus and one as a minus. And difference of two squares will look like that every time. You're adding one, you're subtracting the next time on the binomials. It doesn't matter which one you write down first, but you have to have one of each. Okay, so let's try that same thing here with number 2. Okay, so is it subtraction? Yes, it's subtraction. Are these perfect squares? Well, let's just see. The first one, so we just need our two binomials again. First thing we write down comes from 4x squared. So what times itself gives you 4x squared? Well, that would be a 2 times 2 would give me 4, and x times x would give me 4x squared. Okay? Then we're going to have one where we add and one where we subtract. And then the last number in the binomial comes from the last number up here. So what times itself is 25? Again, I'll color code for you. So 5 times 5. And then y to the 4th, we just got to do split the exponent in half. So half of them go in the first binomial, and the other half go in the second. So this is your set of factors that when you use the double distributive property, end up giving you that to start with. Okay, I'm going to show you over here that it actually does give me my original expression. So here, if you took x times x we'd get x squared. X times negative 3 gives me negative 3x. And if we distribute the 3 times x gives me 3x. 3 times negative 3 gives me negative 9. Every single time, the middle terms are going to cancel out. And the only way that works is if you have one positive and one negative. Okay? That's why the difference of two squares is set up with one addition and one subtraction. All right, we could multiply this one out. Same thing's going to happen. All right, let's do a couple more. So at number 3, I'll go ahead and get it set up. So the first question is it subtraction? And I would say yes, we're using subtraction. Are they perfect squares? Are they perfect squares? In this case, the first term is square root of 16 is 4. Square root of x to the 8th would just be half of that exponent, so x to the 4th. But here, this is not a perfect square. You cannot square root an odd exponent. It just doesn't, you can't split it up into two equal sets. Okay, so this one would be not factorable. One more together. Number 4. Number 4. Looks like we can square root 100. These are even powers, so we can square root those. 9's a perfect square, so we can square root 9. We can square root 2, or an exponent of 2, but this is supposed to be subtraction. This one actually doesn't factor, all right? In order for the subtraction to work, we have to have opposite signs at the end of our two factors. So here, even if I tried to factor this, let's say I tried to do, I tried to do 3z squared and 3z squared, and then I had 10 y to the second. Let me write that a little bigger. Y to the second, p to the 4th, plus 3z, and then we try to do another positive one. What's going to happen is we won't get them to drop out because they're going to have the same sign, like these ones are opposites. Since everything's positive here, it won't drop out the middle term. So this one's not factorable. All right, so check these last 4. I want you to do these last 4 on your own. When you get them done, I want you to raise your hand. I want you to check in with myself or another teacher that's available, and we can get you some feedback and see how they're going for you. All right? Thanks for watching.